All right, howdy everybody. We're going to go ahead and take a look at the extreme value theorem and some of just the little pieces of vocabulary that we have. So I did ask a couple of people, and they felt like sometimes going over the exact same problems we already did is helpful, but sometimes it's nice to do something that's a little bit different. So you're not literally repeating a question you've already seen before. So I decided to go with something that was new. So, well, let's go ahead and see how that works, and we'll talk about our vocabulary as we go and some of those pieces. So let's start off with this thing. Now, so we talk right now about the extreme value theorem. So again, anytime you reference a theorem, it's really important just to remember what that theorem actually has to say. And so I have that sitting right here ready to go. Notice that our extreme value theorem says if f is continuous on a closed interval. Now again, whenever you have what is called a conditional statement, it says if all of this stuff is true. Now, if that is not true, then we are not allowed to use it. It doesn't matter anything else, we quit reading. So the question says, for which of these functions does the extreme value theorem not apply? So does it apply on this one? Well, is it continuous on a closed interval? And I would say 100% yes, but both of these things have discontinuities. So it is not applicable. EVT does not apply on graphs 1 or 2, graphs 2 or graph 3, since the graphs are discontinuous. Now keep in mind that it's discontinuous. This was a jump discontinuity. We just had like a piece that jumped out of, I guess we could call it a removable discontinuity. Even though it does jump up, it's known as a removable. And this was a jump discontinuity. So we're kind of done. Now, when we go into the next little piece, it actually mentions this idea of critical numbers. And so a critical value, I just wanted to remind you again what the definition of a critical value is. I'm kind of thumbing through my notes right here to find our definition of a critical value. So keep in mind that a critical value of a function is a value that is within the domain. That is an incredibly important part of it. It's in the domain where f prime of c is 0 or does not exist. So sometimes we find a value that where the derivative does not exist, but was not in the domain in the first place. And what's kind of funny is sometimes I go through and I find other people's work. And in fact, this is one of those examples where I found a teacher that had worked through this. And I thought, oh, I like the structure of some of these problems, but had errors in their answer key because there was just something wrong. So this particular problem has a critical value right here at x equals -3 because f prime was 0. And that is in the domain and its derivative is 0. We also have a critical value at -1 because f prime of x is undefined. Now, interestingly enough, a teacher that actually worked on this very one and posted online claimed that the number 3 was also a critical value. But we have a problem. It cannot be considered a critical value because it is not included in the domain of the problem. So I must reject that. Now, sometimes those are the easy problems when you actually are given a nice, easy graph. Okay. But this next one, we are in a little bit of a pickle because they didn't give me that graph. Now, what I know about this problem right off the bat is I can take the log of anything provided that it is positive. And I know that x squared plus 4 is in fact positive because x squared itself is 0 or positive. And then if I add 4, the range of this problem would be anything from 4 and up. So I know definitively that the smallest number I would ever take the log of would be 4, which is perfectly fine, or greater than. So the domain of this thing would be all reals. So that certainly tells me that I'm going to have those critical values that I can find. Everything's going to be in the domain. I just have to find out where is the derivative, 0 or undefined. So off we go. Now remember, the derivative of a natural log is 1 over what's inside times the derivative of what's inside. Now, it's a pretty simple little question here, because in terms of where is the derivative undefined, there is no such place. The denominator is positive, so I don't need to worry about any domain issues. But I do need to worry where the derivative is 0. And what I find out is that g prime of x is 0 at x equals 0. So the only critical number that I have is the number at x equals 0. We don't have any undefined values. Now, this is the one that we've actually been kind of trying to stress with you over the last couple of days. And this is what I've been calling, the cusp alert. It is raised to the 1/3 power, which you can do all day long. You can do positives, negatives, you can do 0. It doesn't matter at all. But since it's right now, as it stands to the 1/3 power, its derivative is going to be 1/3 x plus 3 to the negative 2/3 power, or in other words, 1/3 cube roots of x plus 3 squared. Now that looks like a whole lot of stuff there, but notice that I now have a variable that happens to be in the denominator. Now again, I want to know where is h prime of x equal to 0. I want to know where is h prime of x undefined. Where does it not exist? Well, this is not possible. The only way that a fraction can be 0 is if the top is 0, and there is no such value. There is no place where this is true. But even though the function itself is domain was all reals, remember we talked about it, I didn't write it down, but there is a place where the denominator would be 0. Now, I can take the cube roots of positives. I can take the cube roots of negatives. Life is going to be great. I can even take the cube root of 0, except if I were to get 0 in this cube root, I would be dividing by 0. That is a problem. So I definitely have that happen at -3. So my critical value happens at x equals -3. Okay, moving on. Now, this problem's a little bit harder than the previous problems. There's something here that is a little bit less obvious. So I have this question that where I have this function, and I want to apply that extreme value theorem to find the absolute extrema. In other words, I want to find that y value that is actually the biggest value or the lowest value on this interval. So keep in mind the domain of this function. X can be anything within a sine wave. That goes on for all reals. But you can only take the logarithm of positive numbers. So the domain of f itself is x values that are larger than -1. So when we go and we look at this problem right here, I know the extreme value theorem applies. EVT applies because if the domain is everything above -1, this is clearly in that region, since I'm going to say f of x is continuous, and I know that it's continuous because its domain is everything from from -1 to infinity. It's going to be continuous on 1/6 because that's within this domain. So I'm good to go. So all I would need to do to find this extrema is I would need to consider f of 1. I would need to consider f of 6 itself, and I would need to consider any places where the derivative is either 0 or undefined. So let's just see what happens. So again, the EVT specifically mentions the derivative, so let's do that. We have a little product rule. Derivative of the sine is the cosine. F prime g, so remember we're going to think about it this way. Here's f prime and here is g, plus g prime, which is 1 over what's inside, times the derivative of what's inside, or 1 over u du, if you will, times, so this is f prime g, plus this is g prime, but I still need to multiply by f. Now, this is a calculator question because this is just not something we know how to find where this is. I'd love it if I could factor something out, but there's nothing in common. I'm just kind of stuck. So what I did is I typed in my derivative, cosine of x times ln of x plus 1, plus the sine of x on top over x plus 1 on the bottom. Now, I looked at my window and I said, I'm only going to look from 1 to 6 because that was the given interval that we were being discussed in this problem. And then I kind of thought about it, that sine and cosine just oscillate between 1 and -1. So they're not going to provide a huge amount of information. And then secondarily, the natural log of a number between 2 and 7 is not going to be very big. The natural log of like 2 is point something. The natural log of 7 is about a little less than the number 2. So I made a fairly small window because I can tell that these numbers are not going to be very big. In fact, I'm going to skinny it down even a little bit more. And let's just take a look. So this is what the derivative looks like. And remember, I'm looking for where is that derivative 0 or undefined. And you can see that it is well defined. There's nothing wrong. There's no breaks in the derivative. It's perfectly continuous, but it is 0 at these two locations. Okay. So what I chose to do is I put a 0 here because I want to find out where they intersect with the function and 0. So my first number is x. So I'm going to say that f prime of x is 0 at x equals 1.86. No, that's 886. Which, by the way, I think what I would like to do is I would like to store that as alpha a. I'm going to put a little note right there. And then I'm going to calculate the next intersection over here where I get another one. Now, this does take a little bit sometimes because I'm asking it to do some fairly complicated stuff. It's trying to calculate all of those values as it slides. That's why it just goes so slow. And my other number is 4.8099, and I'm going to call that thing B. Store alpha B. Okay, so here's what we're going to do. We are going to look at our values on a number line, and we're going to decide what happened at the endpoints, which is what happened at 1, what happened at 1.866, excuse me, and what happened at 4.8099, and last but not least, what happens at the number 6. So this is how I think I'm going to do that. So again, I stored that information in. I'm going to go back to this original problem, and I'm going to tell my calculator to do the sine of x times the natural log of x plus 1. Let's quit out of there. And then I'm going to do y1 of 1 and see what it says. And it says 0.583. 0.583. Then I'm going to find out what happened at 6. And I got negative 0.544. Let's go ahead and do y1 of a. Now again, those are my critical values. These two right here were my critical values. These were my endpoints, which I had to consider because of the EVT. Y1 of A was 1.008, but I got. And last but not least, I tried Y1 of alpha B, and I got negative 1.751. And so what I could say is by the EVT, the extreme value theorem, let's see if I can move my paper around so you can see it better. By the EVT, there is a maximum of y equals 1.008, or we could say, of course, f of x, at x equals 1.886, and an absolute minimum of y equals negative 1.751 at the value x equals 4.8099, because those were in fact the largest and smallest numbers respectively for this particular value. And notice that I had to use my calculator because I was not able to solve those problems directly. Okay, just a couple more to go. Looks a little deceptive because I got some big boxes here, but those boxes are there because these problems actually took a little more work. So I removed a couple of things from it so that it would fit. So we're going to look at a fairly straightforward problem and then some problems that are maybe a little bit harder. So right off the bat, let's take a look at this guy. Notice its domain is all reals. So again, the extreme value theorem applies. Again, it is continuous on -1, 3. This is a habit of doing mathematics that is very, very important. Same thing is true right here. The EVT applies. Again, this thing has a domain that is all reals, so it's important that we kind of make sure that it's valid to apply this theorem if we're going to do it, because the graph, again, is continuous on -3, 6. This is a step that I personally sometimes struggle with remembering to actually validate that I'm allowed to do that, but it is important. So all we need to do now is we need to consider the endpoints and consider the critical values. So let's go find those critical values. I think you've guessed it. Every time you have nice polynomials, that's the best case scenario. They tend to be a little bit rigged up to be super nice. So I found a quick common denominator to find my two critical values where f prime of x is 0. Those happen at the values where x is 0 and 2. Those are clearly within my region that I'm considering. So let's go ahead and make a quick table of values. So I want to know what happens at the number -1. I remember we have to consider the endpoints. I want to consider 0 and 2 because those are my two critical values, right? And then I also have to consider 3 because that's one of those. Now, without taking a long time to show you all of the math of plugging that in, it's pretty easy to plug it in. -1 cubed, -3 times -1 squared, you're going to get -4. So I've started off with some value, which is actually right now both the min and the max. But when I plug in 0, I get 0 minus 0. So this is now a min, and that is now a max, at least for the time being. But the next person comes in, it's the number 2. 2 cubed is 8. 2 squared is 4. I get 8 minus 12, which is -4. It appears we have a tie. Now we're going to do one more thing, and that is the value at 3 itself. And if we try the number 3 itself, we get 27 minus 27, which is 0. So interestingly enough, we have by the EVT, remember we said we can do that, there's an absolute max of 0 at, now keep in mind that's the maximum is 0, which is literally the value of f of x is 0 at the number 0 and the number x equals 3, and an absolute min of y equals -4, and those both happen at x equals -1 and at x equals 2. So pretty simple little idea. Okay, so for the sake of not making the video overly lengthy, I'm just going to go ahead and end it on the, we're going to do 7 and 8, and I think I'm going to skip one last problem, although I have mixed emotions about that. But we know that it applies, so we're going to have to consider both -3 and 6. So let's see what happens when we take f of x at -3 and +6. I shouldn't have put that there. When I plugged in -3, -3 plus 2 is -1. The cube root of -1 is, in fact, -1. And if I plug in 6, 6 plus 2 is 8. The cube root of 8 is 2. So I clearly have a potential minimum on the left and a maximum on the right, but we'll have to see what happens at those other critical values. So let's see. We're going to go ahead and find G prime. this should be a pretty familiar derivative. In other words, we have 1 over 3, we have the cube root of x plus 2 squared. Pretty simple idea. Now, what I can see is the only place where g prime of x would be 0, because that's what makes a critical value, is if the numerator is 0, which there are none of these. But it is undefined where the denominator is equal to 0. And again, that happens at -2. Now, interestingly enough, although the derivative is undefined, the original function was great. There's nothing wrong with the original function. So if I plugged in -2 into the original function, -2 plus 2 is 0, and the cube root of that is 0. So it is neither the max or the min, it is simply just some other number. So my absolute max, there's a maximum of g of x equals 2 at x equals 6, and an absolute min of g of x equals -1, and that value happened at x equals -3. And what's nice about that, why we keep saying that if EVT applies, is that this just guarantees that not only are those high and low, they're the absolute max. And I don't need to look any further because it literally has to be one of these three values for all questions. Okay, last part of my story, we're just going to go ahead and look at number 9. Just again, just shortening it up ever so slightly. I can take the cube root of numbers. I can do all of this stuff. Again, the domain is all real. So again, EVT applies since f is continuous on -1 to 1. So we know that that's good. So let's go ahead and quickly find f prime, which would be 2x to the -1/3 minus 2. Again, this is fine. This is well defined, but this is 1 over 2 cube roots of x minus 2. Now, again, I now need to decide anywhere where this is undefined and or 0. And clearly I can see that f prime is going to be undefined at x equals 0. So that's going to be one of my conditions that I'm concerned with. I also want to find out when this is equal to 0, and just for the sake of being quick about it, because I'm running out of time, I can tell that that number is going to happen when x is 1. I accidentally put that 2 in the bottom. And you can see that because 2 divided by 1 would be 2. And 2 minus 2 is 0. So I know that f prime of x is 0 at x equals 1. And so what we're going to do really quickly is find out what x and f of x is at the two endpoints, which were -1 and +1, but also consider what happened at 0 because that was the additional place. Notice one of the critical values was actually also an endpoint of the interval. So I plugged in those numbers really quickly. It doesn't take very long to do, but when I plugged in -1, looking back at my notes really quick, when I plugged in -1, I got 5. When I plugged in 0, I got 0. And when I plugged in 1, I got 1. So it appears to me that we have our absolute maximum at 5 and our absolute minimum at 0. And so I think that's where I need to end this thing, and I will see you guys back in class. Have a good one. Bye-bye.